So last we left off on chapter 18, part 1 here. Here's part 2. We're going to start out with the Wittig reaction. In a Wittig reaction, you start with a ketone or aldehyde and a phosphorus ylide to form the alkene. It essentially converts this carbonyl group into a new CC double bond where no bond existed before. And this phosphorus ylide is used as the nucleophile in the reaction. If we look into the mechanism of preparing phosphorus ylide, your triphenylphosphine reacts with an alkyl halide. Here's your nucleophilic attack, kicking off the leaving group. This forms a phosphonium ion salt, which then is reacted with butyllithium, which then plucks off the proton. Electrons go to the carbon. Now this has a negative charge, which then can form a double bond to form the phosphorus ylide. This is under resonance. So this will then form the ylide that reacts with the carbonyl of the ketone or aldehyde. So once you have the ylide, the carbon will attack the electrophilic carbon here, kick off the electrons on the oxygen, forming the beta-ene. The beta-ene oxygen will then react with the phosphorus to form the oxaphosphatane. And then this ring that is formed then undergoes a rearrangement where electrons come down, electrons go up, forming the triphenylphosphine oxide, and then your alkene. An important thing to note is that planning a Wittig synthesis should be done so that you have the less hindered end of the double bond coming from the ylide. So remember that the ylide is made by an SN2 attack of the triphenylphosphine on an unhindered alkyl halide followed by deprotonation. So how would you use Wittig to synthesize this molecule shown here? So we can take our alkene, split it into two parts, one in which you have the aldehyde here and the Wittig reagent on the right, or the Wittig reagent on your left and your aldehyde on the right. You can, either of these are good possibilities. Again, you're going to get both cis and trans mixtures. However, you should be able to draw the forward reactions. So in terms of hydration in ketones and aldehydes, here's a ketone in the presence of water. You can generate a geminal diol, which is a hydrate. While this can happen, actually the reverse reaction is preferred where the ketone form is maintained. So if you have acetone in the presence of water, you generate this acetone hydrate, but again, the equilibrium favors the unhydrated form. In terms of hydration, how it's done, here's an acid-catalyzed version in which plucks off a proton in the presence of the acid. Now water then attacks, electrons go quench that positive charge. Another water will take and deprotonate so that you generate the diol. You can also have it undergo based catalyzed hydration, in which hydroxide attacks the electrophilic carbon, electrons go up. This will then protonate from water, regenerating the OH minus, generating your diol. Cyanohydrins can be formed in which CN groups will come in, attack, electrons go up. This will protonate, right, to generate the cyanohydrin. It's a base catalyzed mechanism that allows this to form. So aldehydes and ketones can react with amines, primary amines, to generate what is called an imine, which is a shift base. Amines are essentially nitrogen analogs of ketones and aldehydes with a C double bond N in place of that carbonyl group. And the optimum pH is around 4.5. So if we look at the mechanism in the next slide, it's an acid-catalyzed addition of amine to the carbonyl compound. So first you get it protonated. This undergoes resonance, right, where your electrons can go over here. And then you have attack of your amine with the electrophilic carbon center. Water will deprotonate, generating your carbonyl amine, right? So it's a carbonyl amine. The carbonyl amine can then react with acid again. This will dehydrate, remove the water, so now you have this. Electrons from that nitrogen come, form a double bond, right? So now you have the major form shown here. This will then deprotonate, generating your imine. An important thing to note is that imine formation is one of the important mechanisms in this chapter. So it's easily remembered as consisting of two simple mechanisms. One is the acid-catalyzed nucleophilic addition to the carbonyl, and then the second is the acid-catalyzed dehydration. So you can have a whole bunch of amines react with carbonyl-bearing compounds. If that Z group was an H, it would be ammonia. If it's an R, it would be a primary amine. If it's OH, hydroxylamine, NH2, hydrazine, NHPH, phenylhydrazine, and then here, this is a semi-carbazide. And you can generate all these products. Formation of acetals, so you can take an aldehyde or a ketone and react them with two equivalents of alcohol, this in the presence of acid. So this would be a acid-catalyzed reaction in which you generate the acetal or the ketal, shown here. In terms of mechanism for forming acetals, at least in this case hemiacetal, you have your ketone react, protonating that, so then you have this in resonance, so then your electrons go to the oxygen, so now you have this electrophilic carbon center over here. Now you have your alcohol react, right, to that center, and then another equivalent of the alcohol will deprotonate, electrons will go. This is your hemiacetal. This is acid-catalyzed. So adding acid to the carbonyl makes it more reactive with a weak nucleophile like alcohol. So we've generated our hemiacetal, and now we want to generate the acetal. So we have the other hydroxide, which will then get protonated. This will leave, and you generate your carbocation. You can have electrons come down, forming the other version, and then your electrons from your alcohol will come in, attack. Now another second equivalent of the alcohol will come and deprotonate to generate your acetal, unprotonated methanol. You can actually reverse the reaction. You can hydrolyze these acetals in the presence of water and acid and regenerate the ketone or aldehyde. Acetals can be hydrolyzed by addition of dilute acids. Excess water drives the equilibrium towards the formation of ketone or aldehyde. Right, cyclic acetals. So you can have the same thing happening, and it's the same mechanism of the acetal formation, but using ethylene glycol, which has a diol, right? And then you have this in the presence of protons or acid. Attack, right? Kick this off. This will then form waters that will leave, so that you essentially form the acetal, the cyclic acetal here. And essentially, These cyclic acetals are used as protecting groups to protect these carbonyl groups when you're doing an additional reaction. So here's a ketone and aldehyde in the same molecule. You're protecting one of them, the aldehyde, with an acetal, so that you can then react the ketone with a different reagent. So in general, when you have both functional groups, the aldehyde is more reactive than ketones. Another important thing to note is that formation of the acetal or hemiacetal does not alter the oxidation state of the carbonyl carbon. In an acetal or hemiacetal, the carbonyl carbon atom is one with 2 bonds to the oxygen. So now you can react the ketone and keep this protected. So if we add sodium borohydride, it'll react with the ketone to the alcohol, and then we can deprotect this by just adding protonated water. Oxidation of aldehydes. So you can take aldehydes, use an oxidizing reagent, and convert those aldehydes into acids. So some of the oxidizing reagents that can be used, and you should note, are sodium dichromate in sulfuric acid, silver oxide in water and THF, and so you can then just take these aldehydes all the way up to the acid. The tolerance test. So the tolerance test involves adding solution of silver ammonia complex, or the tolerance reagent, to the unknown compound. If an aldehyde is present, oxidation reduces silver ion to metallic silver, and you see this metallic silver coat. Reduction reagents. You know many of these. Sodium borohydride can reduce ketones to secondary alcohols and aldehydes to primary alcohols. Lithium aluminum hydride, this is a very strong reducing reagent, so it can also reduce carboxylic acids and their derivatives, which includes esters and acid chlorides. Hydrogenation with a catalyst can reduce carbonyl, but it also reduces double bonds or triple bonds present in the middle. So sodium borohydride, if we take, this is an aldehyde, sodium borohydride, you'll get the primary alcohol, again, ketone, get the secondary alcohol. So it reduces ketones or aldehydes, but not esters, carboxylic acids, acid chlorides, or amides. Lithium aluminum hydride is extremely strong. It reduces aldehydes and ketones, or any carbonyl, because it's a strong reducing agent, and they're traditionally difficult to handle. Now, if you perform catalytic hydrogenation, this is nickel, H2, rainy nickel. We'll take this down all the way down to the alcohol, and it'll also attack double bonds. So the first attack that it'll do would be the double bonds, and then followed by the aldehyde, but it'll attack all of it. Deoxygenation of ketones and aldehydes. So the Clemmensen reduction or the Wolff-Kishner reduction can be used to deoxygenate ketones and aldehydes. So here's ketone or aldehyde, presence of hydrogen to electron reduction, generating the alcohol, right? Then another equivalence of it will remove that alcohol so that it's completely hydrogenated. So here are examples of using Clemmensen reduction: zinc mercury amalgam in acid and H2O. We'll take this, right, ketone, and take it down all the way to the hydrogenated form. Here's heptanal again. It's completely hydrogenated. This cyclohexanone is completely hydrogenated. Wolff-Kishner will take your ketone or aldehyde, reacted with a hydrazide to form the hydrazone. In the presence of base, will take that and completely reduce it to so that it's completely hydrogenated. So here's the reaction, Wolff-Kishner. So you'll add the hydrazide and then heat with base to remove that completely. So you want, yes, it forms a hydrazone, then heat with strong base like potassium hydroxide or tert-butoxide. Use high boiling solvent, ethylene glycol, diethylene glycol, or DMSO, and a molecule of nitrogen is lost in the last steps of the reaction. And so this ends Chapter 18, Part 2.